Okay, perfect. So thanks for the introduction, Thibaut. My name is Patrick. And well, before I start with my presentation, I would of course like to thank the organizers of the DIMACS Workshop and also of the EuroMIDS Europe's competition, which we have participated in. And well, today I'm going to share with you a combinatorial optimization enriched machine learning pipeline to solve the dynamic vehicle routing problem with time windows. Now, this is an extension of the work that we, well, Team Cleopatra, have submitted to the EuroMIDS Europe challenge, where we, well, as Thibaut has already mentioned, won first prize. Now, before I dive into the methodology of our approach, I'd like to take a quick minute to just introduce the dynamic planning problem that was considered as part of the challenge. So basically, here operators need to service a set of requests that is unknown to them at the start of the planning horizon. Instead, these requests arrive dynamically, that is, well, continuously over the planning horizon and are, well, not known to the operator, such that they cannot plan their routes in advance. Instead, they dispatch vehicles at certain fixed points in time, the routes of which cannot be modified after the vehicles have been dispatched. So in contrast to many other dynamic problems, it's not possible to incorporate additional requests into routes of vehicles that have already been dispatched. The objective of this planning problem is then to minimize the total travel time. So we also do not consider service times and so on, well, in the objective anyway, and to service all of the requests. Now, we can formulate this as a decision process where each dispatching decision corresponds to a certain state, which we will also refer to as the epoch instance. This state contains all so far revealed but undispatched requests, which are classified as either postponable or must dispatch according to the time window of the request. So postponable requests could potentially be served in a later epoch, so we can still dispatch a vehicle to them, while must dispatch must be dispatched in the current period because their time window has just advanced so far to the dispatching time that it's not possible to do it otherwise. Then the set of feasible decisions that we have in each state is simply the set of, well, all sets of routes that contain all must dispatch requests and that are feasible with respect to their time windows and the overall vehicle capacity. Now, the system evolves from one dispatching state to the next dispatching state by removing all of the requests that have been dispatched and adding any requests that have been revealed since the last dispatching decision. Here we draw the requests based on rejection sampling from a known request distribution. So this is known to us at well, decision time. We of course do not know which requests will arrive, but we at least know their distribution. Now, the most straightforward way to solve this decision process is a two-stage approach, which basically decouples the request selection procedure from the actual vehicle routing problem. So the idea of this approach is to first decide for each request whether it should be dispatched or not, and then consolidate these requests into routes using, well, or by solving a regular vehicle routing problem with time windows. Now, the drawback of this approach, and this is what Axel has already mentioned, is that it basically decouples the dispatching and routing decisions. So this essentially hides the problem structure, so all the structure that is inherent in the routing solution from the machine learning component that is used to do the actual dispatching decision, such that the machine learning approach is unaware of the consequences or, well, the impact that its decisions have on the actual routing solution. What we need instead is some sort of integrated approach which allows this machine learning component to actually see the impacts that the decisions have on the routing solution and perhaps utilize that structural information. Now, for this purpose, or to implement this approach, we express this dispatching problem as a price collecting problem as price collecting vehicle routing problem with time windows. So this PCVRPTW basically relaxes the request covering constraint and allows to, well, not serve certain requests at all, in contrast to, for instance, a VRPTW, where each request needs to be provided service to. It instead pays a request-specific price upon providing service to a given request, which then transform the distance minimization problem that we have in regular vehicle routing to a profit maximization problem, which essentially tries to maximize the difference between the total price that is paid for providing service to requests minus the total routing cost that is incurred by providing service to those. Now, this reformulation fulfills two fundamental properties. First, feasibility. That is, by assigning sufficiently high prices to must-dispatch customers or requests, we ensure that every decision of this PCVRPTW is actually feasible with respect to our decision process. We also have the optimality property. That is, we can prove that for each or for every optimal dispatching decision, so for each decision an optimal dispatching policy would take, there exists a vector of prices such that solving this PCVRPTW to optimality yields this optimal, or yields a decision that is that equals this optimal decision. So ultimately, our decision problem for each epoch reduces to finding an optimal set of prices and then solving this PCVRPTW. This, however, is the major challenge of our approach because, well, finding this optimal price vector isn't exactly easy. So thinking about it, intuitively, a request's price should roughly correspond to the cost that is incurred by dispatching it in a later period, because that's what we end up serving by providing service to the request now. We do not have to provide service to it at a later point in time. This, however, depends on future requests and is thus impossible to derive deterministically, because it's a stochastic problem. That information is not available to us at decision time. So since we cannot derive these prices deterministically, we try to predict them instead. And this yields the following structured learning pipeline, which integrates machine learning and combinatorial optimization layers. So this is what Axel has spent a lot of time talking about in the previous presentation. So for us, this pipeline works as follows. We start with the epoch instance, which we then feed into a machine learning predictor, which predicts prices for each request. We then forward these prices with the original instance to a combinatorial algorithm, that is our PCVRPTW, which then yields a set of epoch routes which we can just dispatch without further modification. Now, two fundamental questions remain. That is, first, how do we learn the prices? So how can we predict, or how can we train our predictor to predict the correct prices? And how do we actually solve the PCVRPTW? Now, concerning the latter, we implement a meta-heuristic that bases on the hybrid genetic search implemented in Kuhl et al., which is what Wouter has talked about previously in his excellent presentation, and it bases on the implementation of Thibault. And here we modify this algorithm by essentially relaxing the giant tour genome to allow certain requests to not be included inside of it. We implicitly treat these requests as not being provided service to in the final solution. We then modify the crossover operators such that they maintain the request set serviced by the first parent, add additional mutation operators that randomly remove and or insert requests in order to diversify the request set, add additional local search operators that remove or insert single requests according to the detour that they cause. So this is just part of the local search. And further implement an optimization algorithm which batch removes all unprofitable requests and then reinserts all profitable requests. We allow to perturb, or we sometimes perturb the costs here, that is the removal and the insertion costs, in order to further diversify the request set if this is necessary. Now, with this in mind, we can focus on the machine learning layer of our integrated pipeline. Now, for this purpose, assume that we know the optimal dispatching decisions and the corresponding epoch instances. Now, it's important here to always consider pairs of these because, of course, the epoch instances depend on the dispatching decisions that we have that we did in the earlier or in any earlier epoch. Now, our goal is then to train a predictor such that the output of our pipeline, that is the PCVRPTW solution, matches the routes the optimal dispatching policy would dispatch, which is essentially a learning by imitation setting, as Axel has outlined earlier. Now, as our data set, we use these pairs of epoch instances and optimal dispatching decisions and conduct training by simply evaluating the forward path of our pipeline. That is, first predict the prices and then solve the PCVRPTW for these prices, and then backpropagate the gradient of our loss function. Now, the fundamental question, of course, is how do we express our loss function? This is also what Axel has talked about and basically bases on the Fenchel-Young loss. So what we try to do is we try to maximize or we base our loss on the difference between the profit that the routes output by our policy pay versus the profit that the optimal policy or the routes of the optimal policy pay with respect to the prices that we have predicted earlier. So the idea of this is essentially that the left term is a maximization problem. So we always get a vector of routes that is optimal with respect to their prices. So it really maximizes the profit that is paid, while the routes of the optimal decision will not maximize the profits, and the profit will thus be always be less than or equal to the profit of our actual routes. So as soon as we mismatch or as soon as our predicted prices yield routes that do not match the routes of the optimal policy, we get a positive loss. If instead the pipeline's output matches the optimal decision, we have a loss of 0 because, well, they of course paid the same profits. Now, the problem with this loss function is that it is non-smooth. That is, it bases on the output of a combinatorial algorithm, which is piecewise constant and thus has a gradient of 0 almost everywhere, basically. And here we follow the methodology that was introduced in Dali et al. And add a Gaussian perturbation to our loss function and minimize the expected loss instead. Now, according to Barrett, this loss function is smooth, convex, and also has a well-defined gradient, such that we can use it straightforwardly as part of our machine learning pipeline or our training pipeline, basically. Now, the last question that remains is how do we actually derive the optimal dispatching decisions that we use during training? Because so far we have just assumed these to exist. And here we base on the methodology that Wouter has introduced for the Europe is Europe challenge. So this was called the Oracle solution and basically assumes full information on the request set. That is, it assumes that the reveal times of each request are known in advance, and then simply solves a vehicle routing problem with time windows and release times based on this request set. The reveal times here correspond to the release times of the VRPTW here. This then yields a set of routes where we have several, or we can potentially have several requests from different epochs occurring in the same route. And we can then derive the optimal dispatching decision by simply dispatching routes as soon as possible. That is, if a route has a request of the second epoch, for instance, then we only dispatch it in the second epoch and so on. All right. Now we consider a set of benchmark strategies in order to assess the actual performance that this pipeline yields. And these all base on the sequential decision-making process that we have outlined earlier. So these first decide on a set of requests to dispatch, and then solve a vehicle routing problem in order to actually get the routes that end up being dispatched, or well, to consolidate these dispatch requests into routes. So the greedy policy basically dispatches all requests as soon as possible, that is in the first epoch in which they occur. The lazy policy does the opposite, that is it dispatches only must dispatch requests and thus delays requests as long as possible. The random policy dispatches or postpones requests at random, and the rolling horizon policy is a bit more sophisticated in that it attempts to introduce the knowledge that we have of the request set into the decision-making process. It basically samples a scenario for the remaining epochs, quite in a similar fashion as the anticipator strategy does, and dispatches all requests that share a route with a must dispatch request of the current epoch. The Monte Carlo policy attempts to improve on the rolling horizon policy by hedging against outliers. So it basically runs the rolling horizon policy 9 times and then does a majority decision for each request. So if a request occurs or is dispatched more than 4 times, then it also dispatches the request and otherwise postpones it. We also include this anticipator strategy that we use during training and report our results based on the relative gap to this anticipative strategy. Now, to evaluate these benchmark strategies and our pipeline, we run 25, or we consider 25 different request distributions, which we sample 20 times each, and always report the average over these 20 samples. We draw 100 new requests each epoch, and consider a decision time limit of 90 seconds for greedy, lazy, random, and MLCO, so our pipeline. 600 seconds for the rolling horizon policy. We do need to increase the time limit here a bit because we solve fairly large instances if we draw a complete scenario. And 5,400 seconds for the Monte Carlo policy. Now we train our MLCO or integrated MLCO pipeline on 15 request distributions with a total of 79 epochs, so less than we actually use for the evaluation. The instances that we use for training are also smaller than the ones that we use for evaluation. Here we only draw 50 new requests each epoch. We consider a 90-second decision time limit as for evaluation and limit the time of the HGS used to derive the optimal solutions to around 1 hour. Now, our results indicate that our integrated MLCO pipeline outperforms all of the benchmark strategies. That is, we reach a gap to the anticipated strategy of 5.15%, while the next best strategy, that is the Monte Carlo strategy, reaches a gap of around 7%, while of course taking 60% or 60 times the runtime of our MLCO policy. Now, concerning the variance of our objective value across different distribution or different samples of the same distribution, we see that the Monte Carlo and rolling horizon policies actually outperform our MLCO pipeline, even though our MLCO pipeline actually produces a better overall objective value. So this indicates that the machine learning component in our integrated strategy manages to balance basically the trade-off between robustness, which this variance is a proxy of, and the solution quality. Now, we also consider, or we also attempt to investigate several effects that the training procedure has on the performance of our MLCO pipeline. So specifically in the first experiment, we vary the number of instances that we use during training, and we see an unsurprising trend. Well, the more instances we consider during training, the better the performance of our integrated MLCO pipeline. However, we do also see that this effect wears off rather quickly. So at around 10 to 15 instances, adding additional instances doesn't really improve the pipeline anymore, which indicates that a small training set already suffices to learn to train the predictor to predict prices that generalize well to unseen request distributions. Now, varying the epoch instance size that we use to train our MLCO pipeline, we see a somewhat unexpected result. So if we consider instances where we draw fewer than 50 customers per epoch, we see that the performance of our integrated pipeline degrades. The same happens if we increase the instance size beyond 50 customers per epoch. This is a bit unsurprising because especially if we consider 100 customers per epoch, which is the same size that we use for evaluation, we get a significantly worse performing predictor. So it appears that small instances fail to generalize, so we kind of extract too much structural information, while for large instances, just the variance of these instances fails to provide enough structural information to our machine learning predictor. So it's crucial to balance the variance of the instances when we train these MLCO pipelines. Now, if we vary the runtime limit and thus the solution quality of our of the solutions that we attempt to imitate, so by basically increasing the runtime that we account for the offline solution, we also get a bit of an unexpected result. So what we would expect to see here is that with increasing quality of our anticipative strategy, so of the target solutions that we imitate, we should actually see an improvement in the performance of our MLCO pipeline as well. But this isn't the case. It's pretty much all over the place, to be honest, which kind of indicates that the anticipative strategy may not be the best policy to imitate in this particular setting. Now, using different feature sets for prediction, what we wanted to try to do with this experiment is basically just test how much our policy relies on this knowledge of the request distribution. And for this purpose, we consider 3 feature sets: the full feature set, which is used in our baseline as well, a model-free feature set, which simply bases or where all features can be computed from the current state alone. That is, we do not take the request or the request distribution into account for our features, and a model-aware feature set where we only consider those features which can be computed from the request distribution. And here we see that we almost achieve the same performance when using the model-free feature set versus the full feature set, and that the model-aware features actually do not contribute significantly to the performance of our pipeline. Now, as a final experiment, we have tested different types of statistical models. First, a linear approach, which performs the worst, a linear predictor, which performs the worst. Then 3 types of feature-generating predictors. First, a neural network, and then 2 kinds of graph neural networks. The sparse graph neural network appears to perform the best. This is basically a graph neural network which only considers or which only contains edges which connect 2 feasible requests. So we only have an edge if the time windows of those requests allow those to be served in sequence. The neural network is just a feed-forward neural network with 4 hidden layers comprising 10 nodes each. And the graph neural network is the full graph neural network. So in general, what we see is that the performance of the GNN and the regular neural network is almost on par. The only thing that's really important here is that we use some sort of feature-generating model. This may, of course, be related to the features that we use, but we have figured out that this neural network is the way to go, basically. Now, to conclude the talk, we've basically presented a novel CO pipeline to solve this dynamic vehicle routing problem with time windows, which integrates machine learning and combinatorial optimization by reformulating this sequential decision-making process as an integrated PC-VRP-TW. So our results show that the solution from this MLCO pipeline has a gap to the anticipative baseline solution of around 5.15%, which indicates, and this is really the important part of the presentation, which basically indicates that in contrast to what we know or what has been assumed to be common knowledge about multi-layer stochastic optimization problems, imitating an anticipative strategy can actually work well in certain settings. And this is really one of those settings where we see that it appears to work particularly well. Now, regarding research perspective, we're currently working on refining the policy to imitate, that is specifically try to move this problem to a learning by experiment setting, for instance, using reinforcement learning, and possibly applying this integrated MLCO methodology to other problem settings. Now, thanks for your attention. You can find the source code and a paper which describes our approach in more detail by following these links. Thank you.
Thank you so much, Patrick, for the presentation. So we have time for a couple of questions. Yes?
Hi. So on your last slide, you mentioned the gap to the anticipative strategy of around 5%, and concluded that you can imitate learning from the anticipative strategy is a good thing because the gap is small. So in this case, you can consider this gap as sort of the EVPI, right? The value of perfect information. So if you had perfect information, you'd be able to improve for the 5%. How do you see this working in more complicated stochastic problems where the EVPI can be much larger than that? So do you still think that imitating the anticipative strategy could be a good way for training this pipeline?
I think it's something that you could try. Regarding the performance, I'm not sure how that would lay out, of course, but I definitely think it is a promising approach.
That was a question.
No, yeah, I'm
Okay.
thank you for the answer.
So I found it interesting that as you optimized these sort of full information solutions, you got degrading quality. We've seen this in the past in a different context of work that I was doing on rollout algorithms, because essentially you're optimizing, you're overfitting in essence, right, with those solutions. Did you try anything to maybe get worse solutions to see if it, with those full information cases, to see if it would improve performance?
Well, the results that we get from using these 60 seconds are already pretty bad. So I haven't plotted the objective values here, but I think it was a difference of 15% to the optimal strategy. So that's already quite far away, or very, very far away from what you would consider optimal in that setting. But we didn't go any further than that. So because we of course had troubles where with fewer or with less than 60 seconds, we actually didn't even manage to find an optimal or, well, a feasible solution at all.
Yeah, I think there's a trade-off between if something's really bad, you get really bad performance, and if it's, as you get towards optimal, it also degrades. So there's somewhere in the middle, and I don't think we know where that is in these kinds of problems. Right?
Excellent. Well, I don't want to make everyone wait. So we had a lot of really good presentation and questions. Thank you so much, Patrick.